Hello everyone, and welcome to the third part of this series about machine learning. This tutorial will be about regression. In the previous lesson, we have talked about prediction types, features, parameter tuning. We talked about KNN algorithm, classification, and testing accuracy. It's a very interesting tutorial, and you can access it by clicking here. We're actually building there a predictive model that can classify and predict if someone makes more or less than $50,000 a year. So let's start the third lesson by going to Amazon Web Services. You can access that by going to aws.amazon.com and go to your console. Then go to EC2. This is the service that we're using. I will be going over this fairly quickly because we have shown this process twice so far in the previous lessons. So if you're not familiar with every step, you can see a much detailed description in the previous lessons. So we'll be launching an instance, community AMIs, IPython notebook server, and that's the public one. Make sure if you don't find this, this AMI, make sure you choose Oregon in here, US West Oregon. Select that, review and launch. Finally go to our security groups. Yes, edit security groups. Open 2 extra ports for ports 8080 and 8000. Review and launch. Choose existing because I have an existing one. Choose an existing key pair. Yes, I acknowledge. Launch. Now we're launching our instance. We can view our running instances from here or from here. This is our new instance. Let's name it first. Lesson 3. Let's access this. Let's access it. We'll copy the IP, and then we'll go to colon 8000. That should open the IPython notebook server. Sometimes you'll have to wait a little bit until it finishes initialization. I think it's still booting, so let's retry. It's taking longer than usual. Anyway, let's check this one too. 80. Yeah, I think it started working. Anyway, sorry, actually to access the IPython notebook server, you use your IP colon 8080, not 8000. 8000 is for the Agenti administration. That we'll see in a second now. The password is Roshan, Roshan. That's the default password. I don't have to remember that. We'll access the third lesson. That might take a second to load. So, and in this lesson, we'll talk about why do we use regression. We'll look at temperature data. We'll see how can we load and analyze this data. We'll talk about linear regression, and finally SVM regression, support vector machine regression. I made this little script to generate this. So you can run the script by hitting Shift and Enter, and you will get this output. It's a link to the Agenti administration interface, and these are the default username and password for them. So let's do that. Understand, confirm. The username is root and password is admin. So let's do that. We will have to keep an eye on our memory usage. We're using a low specs instance, which is within the free tier of Amazon Web Services, so it can replicate everything we're doing in this lesson without going into any paid services from Amazon Web Service. You can get a better instance and do this with the more memory to do any real work, but for the purposes of this lesson, that will be enough. So let's get back to our IPython notebook. So why do we use regression? In classification, we train a predictive model to produce a class or a category. So in the previous lesson, we were predicting whether someone makes more or less than $50,000 a year. That's a class or a category. With regression, we regression is used when when you need a predictive model that produces a numeric value instead of a class or instead of classes. So it will this predictive model will produce a number instead of class. So if we can train it with enough income data like the previous lesson, we can have it actually predict how much someone is making instead of just a class of more or less than $50,000. Unfortunately, I don't have this data. Um, we'll be using temperature data in this lesson. The data that we'll be using is from Climate Research Unit from the University of East Anglia. I'm sure I tortured the name. You can find the dataset on their website. That's their website, and that's a link to the actual dataset that we used. This is a sample of their data. It's a fixed distance separated file, which is a text file. Um, it has a year repeated twice for each year, and um, it reads every month's um, change from the anomaly that they have set. So we can see January, February, March until December. And the last field in here is the coverage of a global surface that they have to construct this number. So they're using 3%. You can see it's becoming 4%, and it's the number is actually increasing through the years. This is from 1851 until 2014. The columns, we've talked about the columns. We have months basically there, and rows, we have odd rows change from not from previous months. Actually, this is changed from anomaly. And even rows, it's a percentage of coverage globally. We'll be processing this data in Excel or Calc. Actually, I used Calc to process this data. You can download the file and save it. Um, um, you'll have to add a new column and average all the monthly anomalies to create an annual average, and you have to clear out those coverage lines, basically all the even lines. This is how I did it actually. um, I filtered out all the odd rows, um, and I added an average basically. um, and the final file is actually available on your instance, the one that you're using now. It's in data, um, temp data. We can see that in here from Magenta administration, file manager. Go to home, Ubuntu, data, and you can see um, temp underscore data dot CSV, comma separated value. Um, so that's the file that has this data in it. We know how did we acquire this data, and what kind of processing we did on it so far. So we'll start the programming part of this. Let's start by importing the required libraries. I'm importing NumPy, Pandas, scikit-learn, and matplotlib, which is our plotting library. We can load this data by reading the camera separated value file, and we'll store this data in a variable called CSV underscore data. So let's execute that, shift and enter. Um, First, we'll visualize the data just to see what we're looking at. So in here, I'm scattering all the annual averages of the anomaly on the y-axis, and the years on the x-axis. Then I'm plotting the same number just to show, just to give this effect. I'm using the average as the color, so you can see a color bar in here that shows you that shows which color represent positive and negative numbers. Um, we can see kind of a trend in here, but we will be studying this a little further. Um, so let's do this with a bar chart. We're coloring all negative numbers with blue and positive numbers with red. So that's what we get. We can see definitely a trend in here, but most importantly, we can um, visualize our data better to further analyze it. Let's look at the final record. The final record doesn't have all the months. It has until April for 2014, so we cannot really use months in a reliable way to analyze this data. Um, So first, let's calculate some variables. We're basically dropping average TSI, CO2, CH4. We'll talk about those further later, but basically I'm serializing all the month numbers. So I get a long list of numbers for each month of each year. So this is what I have in here. and I'm calculating this monthly index, which will show the year with a point representing every month. So let's visualize that. I'm doing the same scattering technique in here. Um, this is um, this is representing every month in our data set. This is the 0 line, and we can see something going like this almost in the monthly, but we'll still be visualizing this further to see if there are any visual clues that we can use. And this is plotting the monthly data using bar chart. Um, we can still visualize a more interesting pattern in here than the one we had with annual. Um, so first, let's see what we can do with this data. Um, if visually you looked at this data and try to predict where is it going, just with a straight line, you will draw something like this, for example. So this is what this algorithm does. It will try to fit a linear model to represent this data. Um, so I'm doing the same thing now with annual numbers, which are the yearly averages, and this is a linear regression for this period from 1851 until 2014. We can definitely see this is going up actually. Um, this is not the most impressive thing that regression can do. It can be fit to do more interesting things, but not with a simple algorithm like a linear regression um, algorithm. So let's do the same thing for monthly data. This will take a few seconds to process because we have more numbers for months. We can still see the same pattern going on with monthly data. Um, with the linear regression, we can see this is going up over our monthly data too. So we will now look at SVM regression. SVM regression is very um, interesting, to say the least, of an algorithm. We'll be looking at one kernel now. We'll be looking at RBF kernel. Um, the thing about SVM, you have to tune its parameters to give you um, good predictive models. So you can tune it to give you long-term prediction or short-term prediction. You can tune it to give you a more accurate number over for any predictive purpose that you have for regression. So we're training three predictive models here. We're fitting them with our data, but they all have different parameters. We're printing their accuracy, and finally we are plotting them on the same chart. So let's execute this block and see what we have. In here we can see our first linear regression, the green one. We can see that we have three RBF predictions, red, yellow, and blue. We can see the blue is a very responsive one. It's a more of a short-term prediction, and we can see we have two long-term predictions, RBF 2 and 3. One is going almost exponential, and the other one is going to more of a big sine wave. Um, we have a way to test many parameters to find the best fit, the best fit for our predictive model. We do that using grid search. A grid search will test many parameters for each, many values for each parameter, and figure out which gives the best results according to any scoring criteria that you want to use. And here we're using R2 because it's regression. So, oh, I executed that already. So it's returning our best estimator, and it's telling us the best estimator had the C value of 1, um, 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 epsilon of 0.01. I was looking for gamma. Where's gamma? And gamma of 0.001. So we had a few values in here, and this is the a way to even further um, um, refine your numbers by basically looking 10% around the numbers. So I'm looking from 10% less to 10% more, and refining our values. So instead of 1, it's 0.93, and gamma is even more refined in here with the 0.009. So let's visualize this one to see our best predictive model. Our best predictive model shows that temperatures are at best stabilizing in the next few years. Um, it's still going way higher than the anomaly, but more or less it's stabilizing, which is not a bad thing actually. So this is basically creating a prediction from a single um, point of data. At least for the short term, this predictive model is predicting doing a short-term prediction and showing it stabilizing. We can build other models that show more of a long-term um, prediction, and it will show one of the predictive models that we had in here, like the yellow or red one. These are more of long-term predictions, but this is just doing regression with one feature. We were just looking at temperatures and trying to predict where are they going. Uh, Usually you need more features. So if you know of anything that can affect temperature, you can add it into your predictive model to have a more informed predictive model. So for the purposes of this, I will be doing forecast for three more features or three more series of numbers. I'll be looking at CO2 level, CH4 level, and total sun irradiance TSI. This data is from the following sources. CO2 and CH4 dataset are from um, NOAA. It's federal agency that provides environmental datasets. And for total sun irradiance, we get this dataset from the University of Colorado. And it's one of their projects. It's called Source, and they're basically collecting information about sun activity. Um, in here, I'm defining um, a function that returns correlation, basically between two series of numbers. I will be using this function later to measure what's more correlated to what we want to predict, which is temperatures. So let's start with the TSI, total sun irradiance. Um, and here we can see our total sun irradiance data. I added a different axis for that. So the one on the right is the TSI axis, and the one on the left is for the temperature anomaly. We can see some um, interesting pattern going on here. You can see a short-term um, pattern, and you can see kind of a long-term pattern. The correlation between this data and the temperature data is 35.2%. This is not really a high correlation, but we know most of the temperature, most of the heat on Earth is coming from the sun. I think it was like mostly sun activity and barely any um, nuclear or nuclear decay activity from um, heavier metals in Earth, basically. So we can see the general trend in this data going to some level with the temperature anomaly, but it's kind of mm, moving away somewhere around 1970 in here. We'll study this more in a minute. Let's look at our other two features. First, we have CO2 levels. This is in parts per million. So we can see almost an exponential line in here, if it's fairly exponential. Um, the correlation between CO2 and oh, sorry, this is CO2 actually. CO2. The correlation between CO2 and temperature anomaly is fairly high. It's 91% actually. Um, the um, the other feature that we'll be looking at is CH4, which is methane. We can see also the correlation between CH4, sorry, CH4 between CH4 and temperature anomaly is 80.6%, which is also fairly high. You can see little bumps in here with matching little bumps in there. You can see this is almost going with that. As it stabilizes, temperatures go down. As it stabilizes, temperature go down. This is fairly correlated to temperatures. We know CH4 and CO2 are both greenhouse gases, so this is why we're studying them when we're looking at temperatures. So we'll be forecasting all of those. We'll be forecasting TSI, CO2 levels, and CH4 levels. One last thing about CH4, this is parts per billion, not parts per million like CO2. So the numbers might look higher in here, but it's actually much lower than this. This is almost 2 actually, or 1.9 parts per million. Anyway, we'll be forecasting all of that. So we'll start by doing a couple of grid searches for TSI to find the long-term and the short-term fit or predictive model for this. And now we'll visualize both of those. This is our TSI data in dashed gray. We can see our short-term model in green, doing the same wave, and predicting basically the wave to keep going the way it is. So and we have our long-term trend or long-term prediction, and it has a much longer wavelength, if you want to call it that. Um, so we'll be looking at those wavelengths. We have our long-term wavelengths equaling 182 years. So the sun goes from high to low to high again in 182 years, and it goes in this shorter cycle every 14 years, from high peak to the second high peak. It takes 14 years to do that. That's all approximately, because I don't have enough data to get a more accurate number. So this is why it's approximately those numbers. Um, then we'll be predicting CO2 levels. Um, we're testing a long range of gamma numbers to see what is the best predictive model for that, and this is our best predictive model. So by sometime around 2024, it will be fairly close to 420 parts per million. It might go beyond that if we looked at a longer time frame for prediction. But it's clearly not a linear thing. It's going a little bit exponential, if I can just judge it visually, which is totally wrong. But anyway, finally, we'll be doing a predictive model for CH4. We're studying also uh, um, a variety of parameters to see the best fit for that. And finally, we're plotting that, and we can see our data in dashed gray and our prediction in blue. And it's predicting that it will still go up for the next few years, then stabilize, then kind of stabilize, and maybe go a little lower, which is a good thing actually. But it's still going up for the next few years, just based on this prediction. Thank you for watching. This is the end of lesson 3. For any questions, please leave them on YouTube as a comment. You can tweet at me, or you can leave it on Google Plus. You'll find the links to those in the description box below. This is a link to the previous lesson, and it was an introduction to machine learning, and it covered also a classification. And the next lesson we'll be talking about clustering. So we will be talking about why do we use clustering, finding centroid, and k-means algorithm. Thank you for watching, and see you next time.